of here. Here we have a container with mercury inside, and we're going to add water to this part of the container, right? So in this part of the container the mercury will go down, and in the other part it will go up, right? So it is a compensation of the volume that is the water occupying in this part, right? So the first question that we have is the distance or the longitude that the water is occupying within the container, and the other one is the height that the mercury will go up after we add the water in this side of the container, right? They give us the density of the mercury. We have also the density of the water, and we have another thing that is the mass of the water that we are going to add in this part, right? So here we have the density of the water, that is going to be 1, right? That is going to be equal, we know that density is equal to the mass over the volume, right? And we know that the volume can be also defined as the area times the large, right? We also know the areas of this part of the container and this part. In this part we have that is 10 centimeters cubic square, I'm sorry, and in the other part we have 5 centimeters square, right? So we know the mass, that is going to be 100 over our area where it is going to be added the water, that is this part, that is 5 centimeters cubic, over 5 times L, right? I'm going to erase this. So if 1 is equal to 10 over 5L, we can pass L to the other side, and then we have and the one we can pass it dividing this part of here, right? So L is going to be equal to 100 over 5 times 1, but it is 5, right? So we know that the large is going to be equal to 20 centimeters, right? So we already solved one part of the problem. Now we have to know the height that the mercury will go up after we add the water, and for that we're going to use the Pascal's law, that is going to be P1 minus P2 is going to be equal to rho G H, right? We have this law that is from Pascal. And okay, right, here we're going to have different pressures, sorry. Here we have a P1 in this part of the container, and in this other part we have also a P1, right? P2 we're going to in this side of the container we're going to put P2 where it is the bottom of the volume that is being occupied by water, that before it was occupied by mercury. So we're going to put P2 here in this part of the container, and in the other side we're going to put P2 the volume in the bottom of the where it was initially our mercurio after it went up. So here we have P2, and we're going to work with this formula, right? We know that this part of here and here are exposed to the air, so we are going to consider that pressure 1 in both sides is going to be the pressure of the air, that is 1 atmosphere, right? So okay, here we have, I'm going to erase this, and I'm going to erase this. So for this part of here, we have that I'm going to first work with this part of the container, and we have that P1 that we already know that is 1 minus P2 is going to be equal. Here in this part we have mercurio, so we have to work with the density of the mercurio, that is here, that is 13.6 times gravity and times the height. We don't know the height, but we're going to put h, right? And well, we have another h here. We have an h that is between the original height of the mercurio and the new height of the mercurio. So that difference is going to be h. That is what we are going to calculate. But in the other side, we have that the volume that was before occupied by the mercurio will go down. So that difference is going to be h2, right? So this h is going to be actually h plus h2. I'm going to rewrite this. It is going to be P1 minus P2. It's going to be equal to rho, that is 13.6 times G, H plus H2. Right? This is our formula for this part of the container. We have another formula, that is, here we have a certain distance that is going to be L, we already know it, and a certain area, right? A certain area A that has to be equal to, I'm sorry, here is not this area times h, right? We have an area here, an h, that must be equal to this part, the area, to h2, right? So we can get h2, we can pass a2 to the other side, and we have that h2 is going to be equal to a h over a2, right? I'm going to erase this part. Right? So we're going to also work with this one, and we're going to apply this in this other equation. So this was for the part of the mercury. For the other part, it is the water. We have that P1 minus P2 is going to be equal to the density of the water, that is 1, times G times H. But here H is going to be L, that we already know, that is 20, right? And we're going to work with these formulas, right? And we can set that if this is equal, then if this is equal to this, we can get out of our H. Our large, we already know that is 20. Like this, right? And here we have H2. We know that H2 is a H over A2. So I'm going to rewrite the formula. It is going to be like this. I'm going to rewrite it. I'm going to rewrite it here. Okay. $20 would be equal 0.6 10.6 plus so it's going to be like this, right? Our 20, that was the large of this part of here. 13.6, that is going to be the density of the mercurium. We have H plus H2, but we know that H2 was H times A over A2, right? So then we can substitute A's, right? We have A here, that the A of this part was 10, 10, and this part of here was 5, right? So we can rewrite this like H 10 over 5, right? Like this. And we can get out, get out the H, and it's going to be just H here, and here is going to be 1 plus 10/5, right? 1 plus 10/5, and we have H here, so we can pass this part of here, and we can also pass this part here, and I'm going to rewrite it. H is going to be equal to 20 over 13 times 1 plus 10/5, like this part here. H is going to be 20 over 13.6 times 1 plus 10/5, right? And our final result is going to be that the H is 0.49